So next we have a lightning talk by Sadaf, Sayyad. She's a data scientist at Intuit and has over 7 years of experience across industries like internet, finance, retail, and manufacturing. She's built AI-driven products using NLP, machine learning, optimization, and causal inference. Sadaf holds a Master of Management in Business Analytics from the Indian Institute of Science, Bangalore. And at Intuit, as part of the AI team, she's working on designing and developing AI driven solutions that power prosperity for QuickBooks customers through delivering benefits like more money, no work, and complete confidence. So, transformer based language models have taken NLP capabilities to new heights. And if that talk was very complex, she'll give you a nice introduction now and cover some brief insights on evolution of language models in the last decade and discuss innovations that have changed the field of NLP and the current state of the art advancements. And she'll cover pre-trained models that are available today for different NLP tasks to be used for document comprehension. Sadaf.
Thank you, Radhika, for that introduction. Really glad and honored to be here to speak in front of all of you. Today's talk, I want to discuss about document comprehension and deep learning techniques that help that. But before we go to that, I want to give an introduction of what are language models, what is the motivation and how this field has grown with newer and newer innovations. And then what are the techniques that are available today, state-of-the-art techniques for us to use for our use cases. So starting from like, what are language models? Like, the first question that comes when we start off with any kind of language processing. So what are language models? Very simple way that it's basically a task of predicting what's the next word given a sequence of words. So more mathematically, what we're trying to do is compute a probability distribution of what would be the probability of a word occurring given a sequence of words. The new word that we would predict would be from the vocabulary that we have of all the words that are available. Now, any system that does this, that's the task of predicting the next word, is a language model. Now, even though this looks like a simplistic task, like, okay, we're predicting next word, how does this, can we use this same technique to solve many other more non-trivial problems? How do we do that? We'll come to that in the later slides, like how this same task can be then extended to other downstream tasks. Some realistic examples that we are all aware of in real life, like we want to do the next word prediction in our emails and text messages and all, then figuring out what is the tone of an email, when we write an email to someone. Another very important task is the machine translation, where language to language translations. So, okay, we now know what's the task at hand, like what we want to model, and we also know what kind of real examples are there. I want to touch a bit about how this language models have evolved before we go to the and drive the motivation for how the state-of-the-art techniques have come into picture. So starting off, the most earliest techniques has been n-grams, where we have the corpus of text data, where it's a vast amount of text, and we see that for this example, let's say there are 3 words here. What is the probability that the fourth word is books, given that the first 3 words were students opened there, right? So now n-grams is this probability, but there are 2 major problems with this technique. One is storage. We need to store all these 3 phrase words and the what word comes next, and that doesn't scale well, because the moment you have a huge corpus, this storage is going to be a big challenge. The other problem with n-grams is sparsity. Each phrase is very different. It's treated very differently, even if it would mean the same thing. And a phrase like this, or a student opened there, will not necessarily appear in many number of times, and so would be the case for any specific text, right? So these 2 problems were then solved with in use of RNN. RNN are pretty cool. They are used for many other applications, but at the same time, for where the sequence of an event is important, like stock price prediction, right? But at the same time, they are also are used for language modeling, where here the words are sequentially passed, and we're trying to predict either the next word or even the sentiment of that particular uh, phrase or the sentence that has been passed. Now, RNN also has its own set of problems. Very common one is the vanishing gradients. The other problem that RNN has is that it gives a lot of weightage on the last few words. So if there is if there are two sentences like I have lived in France for 1 year, and that's where I picked up French. So now the prediction of the word French is actually very much related to the word France, which occurred in the previous sentence. And that relationship is difficult to capture in RNN because it gives more importance to the last few words. These two problems sort of is trying to be tackled by LSTMs, where LSTM has this feature of forget gates and update gates, which tries to eliminate or at least reduce the importance of words which are not really impacting the outcome, which let's say in our case could be the next word prediction. So if it's not going to impact our next word, where the weights are reduced. But at the same time, LSTM is also a sequential model similar to RNNs. Next innovation, that is the word embedding. Even though word embedding are not particularly for the task of next sentence prediction, what it inherently is trying to do is use of neural networks to capture the relationship between different words, which might have the similar connotation or similar meaning and things like that. So for example, in the left side, if you see one hot encoded vector, so English language has almost 170,000 words. If we were to do one hot encoding, we'll have a very huge dimension vector. But a word like cat and kitten, even though they would be very different, treated completely different in a one hot encoding vector, but these words actually don't mean something very different. And this factor is then captured by the neural network, which is which does the word embedding and reduces the dimensionality for from more than 1 lakh to 700 or in that range, so that these relationships are captured through word embeddings. The other motivation that I want to drive is attention. Now, when as humans, we try to translate from one language to another, we don't give focus on each and every word when we are translating it, but rather we pick the keywords and pay more attention to that when we are translating from one language to another. This similar intelligence is tried to be built in the attention layer, where attention layer is basically for adding weights or giving more weightage to words which do have an impact, or in the task of translation, right? So that however, attention based RNN still continues to be a sequential model. Now, given that these understanding the fact that attention is really important, and giving importance to only the last few words is has its own drawbacks. Now, the next innovation in this field is using the attention layer in the neural networks, but at the same time eliminating the use of sequential models. So this I want to talk a little bit about attention and this particular paper that was published in 2017 by Google Brain scientists, which was titled "Attention is All You Need." The figure on the right side is also from the original paper, which is basically, this is a transformer architecture which eliminates the use of RNN and and LSTMs, which are inherently sequential, and then you instead uses these type of layers. The left side is the encoder and the right hand side is the decoder. What happens is the attention layers are added to the feed forward networks, which builds in the uh, uh, which actually helps learning the models better. This particular transformer architecture is very crucial because this led to the later innovations in the field of language models, that is pre-trained other pre-trained models like BERT and GPT and everything. Okay, now we've seen the transformer models. What is its base architecture? Now how are we going to use this particular architecture and train more models, or how do we use this for a real life examples? Now there's this. Right. So pre-trained models, what are exactly pre-trained models is the models which are built on using on large data sets using self-supervised learning. Now I'll come to what is self-supervised learning, but basically these models are built on a different data set for a different task, but we can continue to use those models for completely different, I mean not completely but relatively different data sets and different data downstream tasks, but it still continues to have that intelligence built in, or of using the pre-trained models. What is pre-trained and fine-tuned paradigm is the same thing, where we build the model for a different data set and then fine-tune it for a specific task that we have at hand. Now, one of the important things is self-supervised learning. Now, okay, now since transformer based architecture is so huge and we have more than 1 million, and in fact some models have 1 billion parameters to train, we cannot have so much data set, labeled data set, that that is available to train all this data, and that brings a big challenge because labeled data is expensive and not available. But how do we go around that is we use something called self-supervised learning, which is we have a huge corpus of data and we use that as an input and output in such a way that there is no need of an additional labeling effort. So for example, the task like masked language model. Masked language model is where we have first we input the sentence to the model, but some of those words in that sentences are masked. The model is not given that as an input, but it's an output, and the task for the model is basically to optimize in such a way that it tries to predict what is that masked word. The other task that is typically given for pre-training these models are next sentence prediction, where next sentence prediction is where we give the first sentence and the model has to predict the next sentence of the as in the next sentence is the output. Both these tasks seem like okay, very specific and narrow, but we can see in the next slide how we can extend this to a different task which is more realistic. But before we go there, what are the different types of pre-trained models? We saw that pre-trained models are built using the self-supervised learning method. Typically, these models are categorized into 3 types, which is encoder only model, which is like, okay, we have an input a passage or a sentence, and we want to identify whether, let's say, classify it whether it's a positive sentiment or not, or any type of classification task or summarizing task. The decoder only model is where you can only see what has happened in the past, like you're given an n sequence and you want to figure out what's the n+1th word. That's decoder only type of models. Encoder decoder is when you have the entire phrase from one as an input, but you have to decode completely different. So like, let's say machine translation, any translation task would be a transformer based encoder decoder model. So there's a list of many models that are available, pre-trained models, which are highly useful. Okay, now in the previous slide, I talked slightly about encoder models. One of it is BERT. BERT is very effective in because it can then be extended to many other downstream tasks. So BERT model is basically pre-trained for masked language as well as the next sentence prediction. We have this weight training, but its use does not stop there, because BERT can then be used for many other downstream tasks like question answering. So question answering, I'll talk a little bit more on it. So question answering is basically you learn the model on this pre-trained tasks, and then give it another data set, which is a list, which the data set has passage, the question that has been asked on that passage, and the answer also lies within that same passage. So the model is basically to figure out where is the answer in that particular package given that particular question. So that's one of the downstream tasks, and you can see that there are many other downstream tasks that can be used or solved for using the BERT model. Right. So just quickly to conclude, how and where we are using some of these models within Intuit. That is the we have projects like where we are answering the question. Customer asks a question like what has been my revenue in the last 3 months, and the question, and we want to fetch that answer from based on the data that the customer has in QuickBooks, and talk about that and give that as an answer. The other is, let's say the customer has, we have a feature where customers can upload some of the documents that they have, and based on the document, there are certain actions that have to be taken, or the resolution of a problem that has to happen. We are trying to, we are working on, figuring out what kind of document that they are uploading, and then based on that, what kind of resolution that needs to be taken by extracting some of those fields and take that particular action. The other very good use case is summarizing audio calls. So customers typically, if they face any issue, they call the support team, within Intuit, and some of the times when there are repeated calls, they have to repeat the entire problem. But instead, if there was a summary note that was captured when the first call happened, and then it makes it much easier for the next customer service agent to talk about, to give them a better resolution to their problem, as compared to if it's manually written notes, or if it's no notes at all, like we're not repeating all of that. Yeah, that's like an overview of what language models are. Thank you. Yeah, any questions?
Hey, hi. Pretty interesting. So, I had a question regarding receipt extraction, right? Because it's usually a semi-structured document,
Right.
and it does. You don't usually have a layout or a template. So, how have you guys gone about it? Because language models, to some extent, only can help with it. And can you like throw some light on it?
Right. Okay. So yeah, receipt extraction, typically the target that we are trying to solve for is when the customer wants to upload a receipt, and then take that as an expense in the QuickBooks, so that we are minimizing the data entry part of it. So most of the times we are more interested in the final number, and that's what we are trying to solve for, like picking the final number. A lot of it is also OCR driven, where the customer is uploading an image, and then we are trying to get the text out of it, and then capture the get that specific output. Yeah, so that's that's the whole idea. Internally, what is a specific use case, that's another team that works on it, and we can talk about that offline as well.
Cool. So my question was regarding the entity extraction part of it. If you can also touch upon a little bit about how do you guys, even curate your data set, right? Because that'll be a good learning for us too. Because especially love to know how Intuit does it. You don't have to go into the specific details, but at least some kind of broader strokes.
Okay, so can you highlight that?
I can just, I think if you look at receipt extraction as such, I mean, one of the things that we require is, label data as usual for any of these transactions as such. So we have a mix of, actual people who label some of the data, as well as algorithms that basically, extract stuff. Now, what we have is we kind of like have both the systems in place. So because, we are actually serving live customers who depend upon us. So we cannot have algorithms like extract the Kong information and populate their books and so on. So to ensure that we basically have a team that basically like a Turk that kind of like extracts stuff. Now, what our algorithms does is that we do a lot of routing. So if a particular receipt looks very difficult to extract, for example, we automatically route it to somebody who can take a look at it automatically. If not, we are very confident that we can extract the information, then it automatically goes. Now, a lot of effort that we end up doing is that we want to minimize the amount of time it goes to the manual routing as such. So that's one of the optimization problems that we end up solving. The second part of it is that a lot of these OCR models and generic models that end up being built outside are very domain independent.
Right.
Now, what we end up doing is that in Intuit is that we also need to start training these models with a lot of domain specific context. So for example, we know what are all the typical customers or vendors that a customer ends up paying, right? So can we use that information to develop a prior that helps us improve upon these models as such? And that actually makes a significant difference to the accuracy that we end up seeing.
Do you guys use any layout LM model or T5?
Yeah, we do use some of them. But then, as I always say, I mean, it's like, and this is very interesting, is that many of these machine learning models, they look very good when published. When we actually end up using it for serving live use cases, it's a completely different story.
Got it.
It's never the case that we can take a GitHub repo and start
Yeah.
using it. It never happens as such.
So we had a similar problem with menus in Swiggy, and it's all Indian cuisine, right? So it was always an issue.
Right. Yeah. We did try out layout model for some other project that we were working on, and the issue is that it's very difficult to get the label data set for the specific use case that we are handling. And layout LM model, in fact, requires the specific answer to be present in that, and a lot of it